Hey everybody, Trey here, and welcome to my 2025 tornado season forecast. We're just a couple days away from the beginning of meteorological spring, and I know many of you are itching to know what this spring might entail tornado-wise in the US. In this video, we're going to dive into that very question in detail. By analyzing several different modulating factors and analog years, we're going to make a forecast for tornado frequency and distribution in the US for the March through June timeframe, which is the climatologically favored period for tornado activity in the US. We're not looking at severe weather as a whole, hail, wind, etc. We're forecasting how many tornadoes are going to occur and where those tornadoes are going to occur relative to normal. Also, we're going to confine our analysis domain to areas that typically see tornado activity on a somewhat regular basis, essentially the plains, the Midwest, the Mid-South, and the Southeast. Last year's forecast for an active to hyperactive spring, particularly across the southern plains and Midwest, went well, and we ended up with one of the most active years on record for tornadoes in the United States. Let's see if we can make another successful forecast this year. As always, I'll put links to any websites or journal articles I mention in this video in the description box below so you can do some research on your own. Also, keep in mind that this is not an exact science. Tornadoes are hard to predict just a few hours ahead of time, let alone months in advance like we're doing here. And as we've discussed on the channel ad nauseum, tornadoes are often influenced by features that occur on a much smaller scale than the modulating factors we'll be discussing in this video. But we can at least make a highly educated guess regarding what might happen this season based on the factors we'll discuss, which have been shown in peer-reviewed research to impact tornado frequency and distribution in the US on some level. So without further ado, let's go ahead and get started. First, let's see where we stand so far in 2025. Similar to last year, we're currently sitting just below average for the year. It's been a relatively quiet start to 2025 with just a small handful of days here and there contributing to the tornado count. Without our sequence of events around mid-February, we'd be well below average for the year. As is typical, the vast majority of tornado reports have been confined to the Mid-South and Southeast. By this time last year, we'd already seen some activity make its way into the Midwest and Great Lakes states. Alright, let's dive into our modulating factors. If you've watched my seasonal forecasts before, you know we look at three main factors that modulate tornado frequency and distribution in the US: global climate teleconnections, sea surface temperature anomalies in the Gulf, and drought in the elevated mixed layer source region. Let's start off with global climate teleconnections, and we're going to use one in particular called the El Niño Southern Oscillation, or ENSO. ENSO involves sea surface temperature anomalies in the equatorial Pacific, basically the departure from average of the sea surface temperatures in the portion of the Pacific Ocean that lies along the equator. As you may know, ENSO has different phases. In basic terms, if the sea surface temperatures in the equatorial Pacific are warmer than normal, as in the top panel, we are in an El Niño phase, whereas if the sea surface temperatures in the equatorial Pacific are cooler than normal, as you see on the bottom, we are in a La Niña phase. And if the sea surface temperatures in the equatorial Pacific are about average, we are in a neutral phase. Now, there are several indices one can use to quantify ENSO phase, and perhaps the most common is the Oceanic Niño Index, or ONI. The ONI is a 3-month running average of sea surface temperature anomalies in the Niño 3.4 region, which is the portion of the equatorial Pacific between 5 degrees north and south latitude and 120 and 170 degrees west longitude. Again, the ONI uses a 3-month running average, which means that instead of measuring the sea surface temperature anomaly in each individual month, the ONI averages the sea surface temperature anomaly over each consecutive 3-month period. For example, January, February, March, then February, March, April, then March, April, May, and so on. This helps smooth out random fluctuations that might occur in the data. If the ONI is greater than positive 0.5 degrees Celsius for a single 3-month period, we would be in a warm phase, and if the ONI is less than or more negative than negative 0.5 degrees Celsius for a single 3-month period, we would be in a cool phase. And if the ONI is between negative 0.5 and positive 0.5 degrees Celsius, we would be in a neutral phase. If we're in a warm phase for more than 5 consecutive 3-month periods, we'd be in an El Niño. If we're in a cool phase for more than 5 consecutive 3-month periods, we'd be in a La Niña, and the same thing applies for the neutral phase. Of course, ENSO is a cyclic phenomenon, hence the name El Niño Southern Oscillation. We oscillate back and forth between El Niño, neutral, and La Niña phases, as you can see on this graph of ONI dating back to 1950. Here's where we stand currently with sea surface temperature anomalies across the globe. Yellows, oranges, and reds indicate warmer than normal waters, while the blues indicate cooler than normal waters. In our Niño 3.4 region, we see mostly below average sea surface temperatures, which indicates that we're transitioning into a La Niña phase. We do see some neutral to above average anomalies creeping in, so this appears to be more of a weak La Niña rather than a strong one. This is a stark change from where we were at this time last year, when we were entrenched within a strong El Niño. However, we transitioned into more of a neutral phase during the spring, which is where we've remained since then, although we continue to see a steady decrease into negative sea surface temperature anomalies this winter. This is expected to continue into the early portion of spring, as illustrated by this graph of numerous climate model forecasts of ENSO in 2025, with each successive 3-month period on the horizontal axis and ONI on the vertical axis. Here's the latest ONI observation for November, December, January, registering at negative 0.49 degrees Celsius, and here's the observed value for January only, coming in at negative 0.71 degrees Celsius. So it does appear that waters continue to cool in the Niño 3.4 region, and models suggest that this may persist into early spring. However, many models also have sea surface temperature anomalies inching back into the neutral range by around April and remaining there through much of summer. Of note, the dynamical model average, denoted by the thick brown line, takes sea surface temperature anomalies firmly back into the neutral phase by early spring, while the statistical model average, denoted by the thick green line, keeps us in a very weak La Niña for the remainder of the year. Taking a combination of the two, we'll stick with our assessment of an initial weak La Niña to start, transitioning to neutral by early to mid-spring. This is supported by the Climate Prediction Center's latest ENSO probabilities for the year. Once again, time is on the x-axis in the form of our 3-month periods, and the percent chance of occurrence of each ENSO phase is on the y-axis. The orange bars represent El Niño, the blue bars represent La Niña, and the gray bars represent the neutral phase. La Niña is favored through the February, March, April period before the odds for neutral ENSO shoot up above 60% for the remainder of spring. Remember, these are just probabilities, so the onset of neutral conditions may occur a bit earlier or later than expected, but for now, it looks like that transition should occur around April. So how does all this impact the atmosphere? Well, ENSO tends to modulate the position and amplitude of the jet stream, especially over North America, as you can see on these conceptual models of the atmospheric impacts of El Niño on the top and La Niña on the bottom. Now these graphics show the impacts during the winter, but the same patterns generally hold for spring. In an El Niño phase, the jet stream tends to be a bit more muted and shifted farther south. You can imagine what impact this might have on springtime severe weather as well. A more muted, less intense jet stream during El Niño means a less intense low-level response, and therefore a slightly less favorable situation for widespread severe weather, including tornadoes. On the other hand, during La Niña, the jet stream is far more amplified with a lot more troughs impacting the U.S., which means severe weather, including tornadoes, tends to be more frequent and widespread, even though in the winter those troughs can get shunted off to the east, drying out the southern U.S. And the neutral phase is somewhere in the middle. These ideas have been supported by ample peer-reviewed research, including this paper by Cook et al. 2017, who tried to find a linkage between ENSO phase and U.S. tornado outbreaks in the winter and early spring, basically January through April. Let's take a look at their figure 3C and D, which show normalized tornado counts for both March and April in the U.S. Basically, they split up the area east of the Rockies into a grid, tallied up all the tornadoes in each grid box during each month for each ENSO phase, then divided those counts by the number of months that each ENSO phase occurred during the study period, which was 1950 to 2010. For example, let's say a certain grid box had 10 total tornadoes during all El Niño marches in the study, and that there were 20 marches where El Niño was present during the study period. You divide 10 by 20 to get a normalized tornado count of 0.5 for that grid box for El Niño marches. For each of these figures, El Niño is on the top left, La Niña is on the top right, and neutral is on the bottom left, and the warmer the color of the contour, the higher the normalized tornado frequency within that contour. For March, we can see that during La Niña, normalized tornado counts are elevated, particularly across the southeast. As we transition to April, both La Niña and neutral periods favor enhanced tornado counts over El Niño periods, especially in the plains, as well as the Midwest during neutral periods and the mid-south to southeast during La Niña. If you've watched my seasonal forecasts in the past, you know that we now typically branch off into research by Lee et al. 2016, which looks at how ENSO phase evolves throughout the spring and how this relates to tornado frequency and distribution in the U.S. This research addresses the issue that ENSO phase is not usually static throughout the spring season, and the problems that arise from only using individual ENSO phase during each month. It was quite effective last spring, which fit their early terminating El Niño progression extremely well, and in many ways, the results mirrored their findings. However, this year's expected ENSO evolution does not fit any of the progressions espoused by Lee et al. 2016, which makes this forecast tricky. It may force us to rely on our other modulating factors, analogs, and climate model output more so than usual, and it may decrease forecast confidence overall. As you may know, there are a bunch of other teleconnections that impact weather across the globe, the MJO, the NAO, the AO, etc. The problem with many of these other teleconnections is that they fluctuate on smaller timescales than ENSO, which makes using them as a variable to forecast tornado frequency and distribution months ahead of time, like we're doing in this video, almost impossible. ENSO changes quite predictably, allowing us to get a good picture of how it will evolve many months into the future, making it quite useful for long-term tornado forecasts. Also, based on research, ENSO appears to have some of the strongest influence on U.S. tornado activity of any of the climate teleconnections. Alright, let's move on to Gulf sea surface temperature anomalies. As you may know, the Gulf is the source of our moisture for severe weather events in the U.S. As low-level flow turns out of the south ahead of developing surface lows, that warm, moist, unstable air mass over the Gulf gets transported northward into the U.S. to set the stage for severe weather. We also know that warmer air holds more moisture. Intuitively, if the sea surface temperatures in the Gulf are warmer than normal, the air mass atop the Gulf that gets advected into the U.S. is warmer and can hold more moisture and thus is more unstable, and the potential for severe weather, including tornadoes, increases. On the other hand, if the sea surface temperatures in the Gulf are cooler than normal, the air mass that gets advected northward is less unstable, and therefore the potential for severe weather, including tornadoes, decreases. This is supported by Molina et al. 2016. In their Figure 3, they illustrate the difference in instability anomalies between cooler than normal Gulf waters on the left and warmer than normal Gulf waters on the right. Mixed layer CAPE, which is our main measure of instability, tends to be near or below normal when Gulf of Mexico waters are relatively cool, as shown by the blue colors, and above average mixed layer CAPE is much more widespread when Gulf waters are relatively warm, as shown in red. Currently, widespread warmer than normal waters comprise much of the Gulf thanks to a lack of convective complexes and cold air intrusions deep into the Gulf this winter. All signs point to this persisting into the spring, which may mean more robust instability than is typical advected inland this spring. Finally, let's take a look at drought in the elevated mixed layer source region. If you followed the channel for any length of time, you probably know what the elevated mixed layer, or EML, is. The EML is that layer of warm, dry, well-mixed air that emanates from the higher terrain out west, western Mexico, West Texas, New Mexico, and areas northward, and gets transported atop the low-level moist layer out east amid westerly or southwesterly mid-level flow. This helps thwart thunderstorm development for much of the day until the cap erodes, and it allows instability to build effectively. However, if the EML is too strong, in other words, if that warm layer is a bit too warm, that can make full cap erosion difficult and can thwart thunderstorm development altogether in a given setup. Persistent, intense drought in the EML source region means hot and dry conditions in that higher terrain out west, which can get transported out east and cause chronic capping issues for severe weather events in the plains and Midwest, limiting overall tornado potential. Therefore, we want to see generally limited drought across the EML source region, as that will keep the EML in check, if you will. Here's our current map of drought across the U.S. from the University of Nebraska-Lincoln's Drought Monitor. The darker the shade of red, the more extreme the drought is. As it stands now, we're not doing too bad. We are dealing with some moderate to extreme drought out west in the elevated mixed layer source region, particularly from northwest Mexico into the desert southwest, and across the central and northern Rockies and central high plains. But severe to extreme drought is not overly widespread. Therefore, I'm not too concerned for how this might impact the 2025 tornado season. We've seen a lot worse in recent years. For example, here's the same map from March 2nd, 2021, and if it looked like this right now, I'd be very concerned. You can see much more widespread severe drought across the higher terrain out west, and this was a year that saw a fairly quiet spring season. So, from a tornado perspective, this year's drought situation going into the season looks at least moderately favorable. Now let's look at how drought might evolve through the season. This is the Climate Prediction Center's seasonal drought outlook valid from now to the end of May. Areas in brown are where drought is expected to persist, and areas in yellow are where drought is expected to develop. In some of the same areas where we're currently seeing elevated drought conditions, drought is expected to persist, and, perhaps more importantly, drought is expected to develop across much of the remaining portion of the EML source region and even into the central and southern plains themselves. This is something we're going to have to monitor as the season progresses, and it may lead to some issues with EML strength, especially as we head into the back half of the season. Overall, I'm not too concerned and expect the drought to have only modest impact on EML strength over our typical tornado domain, but we'll have to watch this closely as the season evolves. Alright, now for the fun part. Let's dive into some analog years. That way we can see what happened tornado-wise in years that had similar background conditions. I went through the database going back to 1950 with a goal of selecting years that had similar ENSO progressions, Gulf sea surface temperature anomalies, and drought out west. That means years that started off in a weak La Niña and transitioned to neutral during the season, above average Gulf sea surface temperatures, and what I called moderate drought in the EML source region. I also prioritized years that had a similar ENSO progression in the year prior. In this case, El Niño transitioning into a neutral phase leading up to our brief dip into La Niña to start this spring. Gulf sea surface temperatures were given the least weight in my analysis, as they have the weakest correlation to U.S. tornado activity of the three variables we studied. So if a potential analog year was a good match for ENSO progression and EML source region drought, but not Gulf sea surface temperatures, I still considered it a good analog, although years that showed good similarities to all three variables were considered best. Now remember, this is a subjective exercise. I didn't use some algorithm to pick out these analogs, so there may be some years that I threw out that you might put into your analysis, or vice versa. Just a couple caveats. First, the database of sea surface temperature anomalies only goes back to 1982, so we'll have to disregard Gulf sea surface temperature anomalies for any years prior to this. Also, the archive of drought monitor maps only goes back to 2000, so to analyze drought for analog years, we're going to use something called the Palmer Drought Severity Index, which is a measure of how prolonged dryness or wetness is in a region, rather than a more short-term look at drought as exhibited in the drought monitor maps. The archive of Palmer Drought Severity Index maps goes back to 1950, which is useful for our purposes. For years after 2000, I'll also show the drought monitor map heading into the season. This is our current Palmer Drought Severity Index map. Yellows, oranges, and browns represent long-term dryness and, in turn, drought, while greens represent abnormal long-term wetness. Many of the areas highlighted on our current drought monitor map, such as the Desert Southwest, West Texas, and the Central to Northern High Plains, also appear on our Palmer Index map, meaning that drought conditions across these areas have been festering for a prolonged period. So in comparing this year's drought to that of analog years, I looked for years that had similar moderate, somewhat persistent drought conditions across the EML source region during the spring. In my research, I identified 7 different analog years that had similar background conditions to this year. We'll start with the best analogs first before moving into analogs that are still applicable but not quite as closely matched. The first analog is 1996. After an El Niño to neutral to La Niña transition in 1995, we began the 1996 spring season in a weak La Niña before dipping back into neutral for the remainder of the year. Unlike the forecast for this year, Gulf sea surface temperatures transitioned from slightly below average to average during the season. However, drought was a decent match, particularly in southern portions of the EML source region, which experienced prolonged drought through much of spring, similar to what's expected this year. March through June 1996 ended up slightly below average with only 639 tornadoes compared to the climatological average of about 750 to 800. March came in around average with the vast majority of activity confined to the Mid-South and Southeast. This was followed by an average April which featured a high concentration of activity across the Midwest and Mid-South, along with some activity in the Southern Plains. May was average to slightly below average. Interestingly, much of the activity was shifted slightly farther west compared to normal into western portions of the Central and Southern Plains, along with some activity across the Northern Plains into the Midwest and Mid-South. The season ended with a bit of a slow June, with a smattering of activity from the plains into the Great Lakes. The next good analog is 2006. Although we didn't start off the previous year with as strong of an El Niño as we did in 2024, the ENSO progression matched well with this year's forecast, beginning with a weak La Niña that transitioned into neutral by early to mid-spring. Sea surface temperatures in the Gulf oscillated between average and above average during the season, also similar to this year's expectations, and we began the spring with prolonged drought conditions in southern portions of the EML source region that proliferated into areas to the north as the season evolved. Short-term drought was moderate and encompassed much of the EML source region by season's end. Overall, spring 2006's tornado count was slightly below average, but things certainly didn't begin that way. The season kicked off with an active March that saw around double the monthly average number of tornadoes. But nearly half of this tally came from a single multi-day outbreak centered on the Missouri area just before mid-month. Outside of this, tornado activity was fairly sporadic in frequency and distribution. Activity continued into April, which came in quite a bit above average with a clear hotspot from the Midwest into the Mid-South and Southeast, and only sporadic activity across the plains. April featured multiple double-digit tornado days spaced fairly evenly throughout the month. However, May brought quite the contrast, coming in well below average with only around half the typical number of tornadoes for the month. The plains were extremely quiet, with most of the activity confined to Texas, along with some sporadic activity from the Midwest to the Southeast. June was pretty dismal as well, with only widely scattered activity across the central and northern plains and Midwest. 1967 is another top analog. Although we never truly dipped into La Niña at any point in the year prior or spring 1967 itself, the overall ENSO progression was very similar to this year's. After switching from a moderate El Niño into neutral in 1966, Niño 3.4 sea surface temperature anomalies continued to inch into the weekly negative portion of neutral to begin spring 1967, and we remained in neutral ENSO throughout the season. Again, we'll have to ignore Gulf sea surface temperature anomalies for this analog, but drought was a decent match, with low to moderate prolonged drought across central and southern portions of the EML source region for much of the season. Now remember, tornado reporting and surveying practices were much more rudimentary in 1967 than they are now, so don't pay as much attention to the monthly and total tornado counts for 1967, but rather focus on the areas where tornado activity seemed to be enhanced. March saw most of its tornadic activity across the southern tier of the U.S. April featured a clear hotspot across the Midwest and Great Lakes states, alongside some southern plains activity. Like May 2006, May 1967 lacked any defined hotspots. Aside from Texas, the plains were very quiet. Sporadic activity occurred across the Midwest, Mid-South, and Southeast. However, June was active to hyperactive, particularly in the corridor from the southern high plains into the central plains and Midwest. The next couple analogs are not quite as good as the first three we discussed, but still have some utility in analyzing. The first of these is 1984, whose ENSO progression matched quite well to this year's. However, sea surface temperatures in the Gulf remained cooler than normal throughout the entire season, and nearly the entire EML source region featured no long-term drought at any point during the spring. Both of these matched poorly to what's expected in 2025, but because 1984's ENSO evolution was quite similar to this year's, it's worth discussing. Again, given the discrepancy in reporting practices between this time period and today, and the fact that spring 1984's 705 tornadoes is approaching the climatological average, we can surmise that 1984 was a fairly active season. Excluding the significant outbreak in the Carolinas, March was relatively quiet, with most of the activity focused on the southern plains into the Mid-South. April featured quite a concentration of activity across the central and southern plains, along with some activity from the Great Lakes to the Gulf Coast. Once again, May was relatively quiet on the plains, with the preponderance of activity occurring from the Mid-South into the Southeast, but, like 1967, June was hyperactive with a local maximum from the central plains into the Midwest. 1984 was also our first analog to truly highlight the central high plains, including Colorado and Wyoming, in their traditional time period in June. Our next second-tier analog is 1981, whose ENSO progression was a decent match, aside from a lack of a moderate to strong El Niño to start the previous year. Drought was also a decent match. The corridor from the desert southwest to West Texas featured much less drought than what we have currently, but central and northern portions of the EML source region featured low to moderate prolonged drought. Overall, spring 1981 was perhaps slightly below average for tornadoes across the U.S. March was quite slow, as was April. The bulk of April activity occurred across the Midwest, with a secondary maximum in the southern plains. In contrast to many of our other analogs, May was quite active, especially across Oklahoma and Texas, and June was active as well, with the Midwest seeing a good chunk of activity along with some lingering activity across the central and southern plains. Our final two analogs are the weakest of the bunch, but still hold enough similarities to our current and forecast background pattern to warrant inclusion. 1989 was a good match for overall ENSO evolution, with the previous year starting off in an El Niño that transitioned into neutral and eventually La Niña and back to neutral during the 1989 season. However, from the end of 1988 through the first half of 1989, we plunged into a much stronger La Niña than is forecast this year, which weakens its efficacy as an analog compared to the other years we've discussed. Gulf sea surface temperatures transitioned from warm to neutral to cool throughout the duration of the 1989 season, and prolonged drought was prevalent across much of the EML source region, similar to this year. 1989 was, once again, slightly below average. March was fairly quiet, with the bulk of activity confined to the Gulf Coast states. April mirrored March's below-average tornado count, with only scattered activity across the Midwest, Mid-South, and Southeast. April also featured a 2-week stretch centered on mid-month that featured virtually no tornado activity across the continental U.S. May picked up the slack but still ended up average to slightly below average. Texas saw quite a bit of activity in May, but as in some of our other analog years, many of the traditional plains tornado hotspots were relatively quiet. The central to southern high plains were a clear hotspot in June, which came in above average, and there was quite a bit of abnormal late-season activity across the southeast. Our final analog is 2018, which matched this year's ENSO evolution well, beginning in a weak La Niña and transitioning to the neutral phase during the spring. However, the previous year did not start off in El Niño, and we ended up jumping into El Niño rather than remaining in neutral by summer 2018. Still, our spring ENSO progression was a good match, as were Gulf sea surface temperatures, which remained above average throughout the season, with the exception of May. Southern and central portions of the EML source region saw both long-term and short-term drought throughout the season. You storm chasers out there probably winced when I mentioned 2018, as for many folks, that was one of the more dismal chase seasons in recent memory. Spring 2018 came in below average tornado-wise, starting with a quiet March aside from some activity in the southeast. April was dead quiet for the plains, which went without a single tornado report during the entire month. Most of the activity was confined to the Mid-South and Southeast. While the tornado count slowly increased in May, the month still ended up well below average, and notable tornado events were few and far between. Most of May's activity was confined to the Central Plains. June finished closer to average, but no real hotspots emerged. There's been a lot of hubbub within the weather community regarding the infamous 2011 as an analog. While it does have some decent similarities to our present-day pattern of global sea surface temperature anomalies, I decided to exclude it from my analysis. 2011 did follow our general forecast for ENSO evolution. However, we were in a much stronger La Niña to end 2010 and begin 2011. In addition, we quickly plunged into another moderate La Niña toward the back half of 2011, rather than remaining in or near the neutral phase. This is much more reminiscent of Lee et al. 2016's resurgent La Niña pattern and is not a good match to this year's expected ENSO progression. Therefore, while 2011 is worth perusing, it appears to be an outlier and an analog of low efficacy in relation to our other analogs. Alright, now that we've selected our analogs, let's take a look at the composite upper air pattern in these years. Using the NCEP NCAR reanalysis datasets, I've plotted the composite 500 millibar geopotential height anomalies for all of the 7 analog years that we discussed. I gave extra weight to our best analogs, 1996, 2006, and 1967, so that's why you see those years listed twice on the bottom. Blues and purples indicate lower than normal heights and, in essence, a tendency for increased troughing, while greens, yellows, and oranges indicate higher than normal heights and, in essence, a tendency for increased ridging. We'll start off with the entire March through June period, and right away, this gives you a clue why many of our analog years tended to be below average for tornado activity overall. We see a tendency for below normal heights off the west coast and in the northeast, but, more importantly, notice this area of slightly above average heights centered over the southern plains. This would perhaps be associated with a tendency for slightly stronger ridging than is typical here, meaning less robust troughs impacting these areas, and more storm systems displaced slightly farther north, yielding potentially increased activity in areas such as the Midwest and Mid-South. This really starts to surface in April and May. Here's the map of 500 millibar height anomalies for analog Aprils only, and there's a clear tendency for significantly decreased heights and potential troughing off the west coast, but notably increased heights and potential ridging across the southern U.S. In analog Mays, the area of above normal heights shifts slightly west but would have a similar impact. With below normal heights across the northeastern quadrant of the country, this would appear to invite more northwesterly flow events into areas east of the plains, a pattern often reserved more for the summer, and keep the central and southern plains on the quieter side. Overall, this is a somewhat unfavorable look for an active season across our domain, especially for traditional Tornado Alley. A quick glance at some of our long-range climate models confirms these suspicions. As illustrated in these 500 millibar height anomaly maps, the latest run of the CFS shows at least a somewhat favorable pattern for March, with a hint of troughing across the southern tier of the country. Our latest medium-range models also suggest that March might start off with an active jet stream situated across the southern U.S., which could provide increased chances for severe weather, possibly including tornadoes, to kick off the season. However, according to the CFS, higher than normal heights and a tendency for ridging take hold across the central U.S. for the remainder of the season. The latest 3-month precipitation outlook from the Climate Prediction Center also suggests a bit of an eastward shift to overall precipitation through the end of May, with heightened chances for above-average rainfall in the areas shaded in green, which encompass the Great Lakes, Midwest, and Mid-South. On the other hand, elevated odds for below-average precipitation, shaded in brown, are in place for much of the plains. Now remember, these are overall precipitation anomalies and are not directly correlated to severe weather and tornadoes, but it's at least something to keep in mind as we head into the season. So, with all of this being said, what do I think is going to happen this year? I will say that forecast confidence is a bit lower this year compared to last year given the unique background conditions, particularly in terms of ENSO, but let's give it a shot. Despite the fact that most of our analogs had below average tornado activity across the U.S. in March, our long and medium range models suggest that this may not be the case this March thanks to an active jet stream throughout the month. Therefore, I think March will be closer to average, with most of the activity confined to the southern tier of the country, including the Mid-South and Southeast. I wouldn't be surprised if we end up a little above average, but considering our analogs alongside our forecast model solutions for the next couple weeks, I'm going with more of an average tornado count for the month. April is a little trickier as we have some conflicting signals among our analogs and climate models. Given a tendency for April to be a bit more active in our best analog years, I think April might be closer to average, like March, with the tendency for activity to be concentrated a bit more in the region from the east central plains and Midwest to the Mid-South. We might start to see a bit of a slowdown in activity due to that shift in the background upper air pattern toward a slightly more unfavorable state, but overall I think we see a decent amount of tornadic activity in April, perhaps near average. Unfortunately for storm chasers, May is looking a bit bleaker. Given our analogs, potentially unfavorable background pattern, and worsening drought in the EML source region, I suspect May will end up below average, with many of our traditional peak season spots, such as Oklahoma and Kansas, coming in on the quieter side. Texas still seems to have a decent amount of activity in many of our analog years, perhaps fueled by an abundance of smaller scale or less obvious severe weather events, so that may be a place to watch, along with perhaps some continued activity in the Midwest and Mid-South. As always, tornado activity in June is difficult to pinpoint because our ENSO teleconnection is weakest at this point in the season, so we'll have to rely more on our analogs. Despite a somewhat unfavorable look on climate models, several of our analogs saw active Junes, but specific hotspots were difficult to pinpoint. Leaning into our analogs, my guess is that we'll see an average June. The southern high plains might be a spot to watch based on our climate model output, as well as potentially the central plains into the Midwest, which was highlighted in some of our analogs. Putting all of this together, a near average first half of the season, followed by a slow late April into May, ending with an average June, I think we're in store for a slightly below average tornado season overall. I think a good chunk of the activity will be shifted farther east compared to normal, focusing on the Midwest and Mid-South, while our traditional central and southern plains hotspots will remain on the quieter side. So that's going to do it for this year's tornado forecast. Let me know what you think in the comments below. We'll probably revisit this forecast in a video after the season is over to assess how our forecast performed, so stay tuned for that. Again, forecast confidence is a bit lower than last year, and small-scale perturbations in the background pattern, which are impossible to forecast at this range, can make major alterations to overall tornado activity during the season. Still, I'm happy with our forecast. Even though 2025 may not look the most optimal for storm chasing, there will still be some amazing storms and tornadoes for chasers to experience, hopefully in fields in the middle of nowhere. Thanks for watching, and we'll see you in the next video.